we are going to talk about some properties of eigenvalues in relationship with matrices that you study. For example, remember that we were going and calculating eigenvalues for a matrix. So I might be given some matrix such as a -1, -3, -3, 7. This, you go ahead, find the characteristic polynomial and get your eigenvalues, and your eigenvalues, well, you'll have as many of them as you have number of rows and columns of this matrix. Now there are some nice connection between these numbers and the original matrix that sometimes come in handy. Those two are covered under two titles. One is called trace, which is perhaps new. And the other one is something you have seen before, is called determinant. These two quantities have an easy connection to the eigenvalues. So the title would be trace and determinant in terms of eigenvalues. So first of all, what is trace? Trace of a matrix, very simple. It's just sum of all the terms on its main diagonal. You just add them up. That's called trace. Turns out to be very important. So trace sum of elements on the main diagonal. I said main diagonal because, well, any square has two diagonals in it. The one that plays bigger role is this one. It turns out, with some basic ideas from college algebra, that you can show that the trace of a matrix is exactly the same as the sum of its eigenvalues. Okay, so we have the following theorem. So you don't need to go ahead and do all that work to get the eigenvalues to figure out what the sum of the eigenvalues is going to be. If all you need is sum of eigenvalues is right in front of your face, just add up these numbers, bypass a lot of crud, and then this is sum of. Say it again. We are still in 5.2. We're still struggling with 5 eigenvalues. So this is the very last item in that section. So for this matrix A, sum of eigenvalues, so if you want to do this, you have to figure out what they are. What this theorem says is I can tell you what that is without pushing you to do much of any work. It's just trace -1 plus 7. Not that these are eigenvalues, but their sum is that same as that. Well, let's go and verify just for our what did we do to get the eigenvalues. We said we get the characteristic polynomial that is the determinant of lambda minus a. So you take your matrix, flip all the signs, so it will be 1, 3, 3, minus 7, and then you add the lambda to it. So that determinant is just lambda plus 1 times lambda minus 7, then minus 3 times, what was this? I wrote 3 times, this is also 3. So when you multiply this out, what do you get? Lambda times lambda, that's lambda squared. You have 1 times lambda minus 7 times lambda. Let me write it out clearly. 1 times lambda and minus 7 times lambda. This 1 minus 7 is really the same 1 minus 7 that shows up here, or 7 minus 1 that shows up here. And then we have minus 7 minus 9. So I have lambda squared minus 6 lambda, and then minus 16. What's the factorization of that? Lambda minus 8 and lambda plus 2. How did you find these two numbers? These were two numbers such that the important thing is they add up to minus 6. Is that right? So forth. The sum of, you set this thing equal to 0. You found these numbers such that their sum would be minus 6. Now, what are the roots? 8 minus 2. So what would be the sum of these two? When you are finding roots, you are taking these numbers to the other side. So there's sign has to be flipped version of these. So what's the sum of these numbers? So sum of these numbers is negative of the number that shows up here. Well, how did this number show up here? This number, you remember, it was this minus 7, one of these entries, times lambda, and then plus 1 times 7. That's how you got the minus 6. And then the sum of the eigenvalues just turns out to be the negative of that quantity. So this 6, you can say it again. To get the sum of the eigenvalues, here's a shortcut. You just add up the terms on the diagonal of the matrix. You are all set. You don't need the characteristic polynomial. You don't need to solve any equation. Now these polynomials typically manufactured so that factorization and everything will be easy for them. Those eigenvalues could have been unfriended numbers, the equation, perhaps high order equation you couldn't solve, or they could be complex, or all sort of complication. But none of that shows up here. So figuring out the trace is infinitely easy. Figuring out these quantities in general could be quite complicated. So the theorem helps quite a bit resolving something. So let's state again. There isn't anything special about the 2 by 2 matrices. If it was 3 by 3 or 4 by 4, will be all the same. Sum of eigenvalues is equal to the sum of diagonal entries. Property number 2. Sometimes what you need is the product of all the eigenvalues. A product of eigenvalues, what would be the product here? 8 times minus 2, that would be 16. Now, you can look at it another way. Those numbers that you were finding were being manufactured so that their product will be just this number, like this minus 8 and 2 that you had found. You had found them such that the product will be minus 16. Of course, you are taking them to the other side of the equation, and sign of each of them is flipped over, but the product, since you have 2 of them, the product is still minus 16. Now if you come here, what quantity associated with this matrix is minus 16? What is the name of that? The determinant of that, if you multiply these, it's your minus 7. Subtract this one from it, that's your minus 9. The entry that shows up here is really just your determinant. Why so? Is that accidental? No. If you had set lambda to be equal to 0, this portion will just all get wiped out, and you are just left with that very last number. what is that last number? Would have been the determinant of the matrix that you had to begin with. So what we have here is that the product of the eigenvalues, if that's all of you want, that is equal to the determinant of original matrix. So sometimes a trick equation shows up like this. Somebody might give you some nasty matrix without thinking about designing it so that it will be easy for a student to go find all the numbers. Question?
Is this only for square matrices or all matrices?
Well,
These theorems.
it wouldn't make sense for rectangular ones because we don't have any such thing as a, I mean, our eigenvalues are already defined for why so? Because we want the output of multiplication to be a stretched version of the input. So output and input should live in the same space. I don't want to have a three-dimensional input and say a four-dimensional output. If that was the case, I couldn't compare them. I want to compare them, say what comes out of this matrix is very similar to what went into the matrix. If you want to do that, then it has to be a square matrix. Otherwise, well, you have to define for yourself what is it that you want. So the whole thing, as far as we are concerned, the whole thing only makes sense for square matrices. Also, trace is only defined for square matrices. The same way, determinants only defined for square matrices. So everything here on default is just applicable to square matrices. So what we have, the sum of eigenvalues is just sum of the diagonal entries. A product of eigenvalues is just determinant of the original matrix. So if I give you some nasty matrix like 2, 3, 5, 7, 9, 2, 1, 1, say 1 again, and I say what's the sum of eigenvalues, if you don't pay attention and go spend 15 minutes to figure out, maybe even more than that, or maybe the problem never easily gives you any answer. If all you want is sum of eigenvalues, you just answer it in a matter of a couple of seconds. What is the answer in this case? So this is in this case just 12, as opposed to that maybe 15 minutes, maybe 2 hours to go get the eigenvalues and just add them up and just figure out, well, that was right in front of you. And if you want the product of eigenvalues, so again, where did the 12 come from? 12 came from here. Just take these guys. Product of the eigenvalues, you say, okay, let's copy it over, and so you will have 2, 7, 1, 3, 9, 1, and then you repeat this multiplication 3 times, and then so you have 2 times 9 times 1 is 18, and 3 times 2 times 1, that is 6, and 5 times 7 times 1 is 35. Going backward, you have 45 here, 4 here, looks like 21 here. So it looks like I have 24 and 25. If I have not made a mistake. So the eigenvalues, whatever those numbers are, they add up to 12, and the product is minus 11. And to show the proof of that, you need some basic items from college algebra for factorization of polynomials, and what do the roots of a polynomial have to do with the coefficients of polynomial. This is really the same thing. It's not so special about linear algebra. It's really college algebra. Okay, you're going to rush a little bit and move on to next section. Next section, we have essentially finished this thing. It's called diagonalization. Diagonalization, well, what is diagonal? Diagonal means items on these locations in a matrix. A diagonal matrix is a matrix whose off-diagonal entries are all zeros. So this is a diagonal matrix. So in a diagonal matrix, everything that's off-diagonal is zero. On diagonal, it could be anything. Diagonal matrices are the easiest things to work with. They come as close to ordinary numbers as any matrix could. So if you could take a matrix, push it and shove it until it looks like a diagonal matrix, you have made a significant achievement, because working with matrices, we have noticed, is quite painful. But these are just like ordinary numbers. They don't create any type of a headache. Well, of course, there must be a catch. The catch is that not every matrix can be diagonalized. Okay, not every matrix can be diagonalized. Most matrices, however, can be diagonalized, and the cost of doing that is that you have to get all the eigenvalues, eigenvectors, and do all that work. Once you do it and do a matrix inversion, yes, you have it. So you can do it once and then use it over and over again. But here's the catch. So not every matrix. So some matrices cannot be diagonalized. So the question is, which matrices actually can be diagonalized? There are also extensive theorems to establish that. Essentially, what you need is a full set of eigenvectors to be able to do this. So the condition for diagonalization suppose you have a matrix A, is a square matrix A. If your matrix has a full set of eigenvectors, well, what do you mean a full set? What's not a full set? We looked at some examples last time. Took it like a 2x2 matrix. It had only one eigenvector, nothing else to be found. A full set means the matrix has as many eigenvectors as it's their own dimension. A typical 2x2 has 2 eigenvectors. A typical 3x3 has 3 eigenvectors. If it so happens that you cannot find 3 linearly independent eigenvectors, that is exactly the situation that this dream is not going to materialize. Diagonalization can happen if you have, so if your matrix is n by n, a full set of eigenvectors means n linearly independent eigenvectors. The problem is it's very hard to tell from outset if a matrix has those eigenvectors or not. Like, you really have to go and get your hand dirty, do all the work, and figure out if it has it or it doesn't have it. If it does have all the eigenvectors, then you're all set. So telling something in this case is not as easy as it was over there. Like over there, I ask you what's the sum of eigenvalues. It just takes you a second to say. But here, if I ask you, well, does this matrix, like here, if I said, does this matrix have 3 eigenvectors? So, okay, give me an hour, I'll tell you. It's like, you cannot just look and say. So, what is the process? The process we have just gone through in the last couple of lectures I just mentioned. The idea was that if you take a matrix multiply by one of its eigenvectors, what happens? What's the special thing that happens with the eigenvectors? It just gets stretched, is that right? It gets stretched by some factor, and the factor is just shown by lambda 1. If you multiply it by the second eigenvector, what happens is that that eigenvector gets stretched by some factor, and so on. Suppose that we actually do know that our matrix really has all the eigenvectors that we need. It has all the n eigenvectors. In that case, you have all the way to the very last of these eigenvectors, you have the same relationship. And these eigenvectors are linearly independent. So you're not trying to sell me something, trying to cheat me by saying, okay, I just give you same eigenvector a second time, or I just double it and give it to you again. No, none of that. The eigenvectors have to be truly independent from each other. Well, what did we say we can do? How can we summarize all of this? So a good way to write this is, okay, take your matrix. So here's your matrix A. All of these eigenvectors, how did we line them up? So this was a square matrix. So okay, take your V1, just plant it here. Like, occupy a whole column with your V1. If you take A, multiply by V1, out comes a stretched version of this, perhaps double as long, maybe triple as long or something, but let's hold on for a minute. We go ahead, plant V2 right next to it, and so on, all the way to the very last of these things. We just string all of these eigenvectors one next to the other one. When I multiply them, what happens? According to these relationships, what comes out is, if I take this matrix multiplied by V1, all I get is same matrix multiplied by some number. If I multiply by the second column, I get stretched version of that one, all the way until the very last one. Last one also gets multiplied by some number. Okay, what did we say? This is something hopefully you remember from the beginning of the semester. There's a way of factoring this matrix. So this is same as taking that matrix of all the eigenvectors and then multiplying it by what? Or just lambdas. And we have to be careful that the lambdas have to be on the right, not on the left. If you put all of your eigenvalues here, you have exactly what you need. That is A. This is your matrix A. Capital V, I'm going to show the collection of all the eigenvectors. You have just planted them one next to each other in vertical fashion. On the right hand side, we have exact copy of this guy again, and we have this particular matrix, which is a diagonal matrix. That's why this topic is called diagonalization. Diagonalization because this is diagonal. On the above and below the diagonal is all zeros. So what we have, the diagonal matrix, we said we write it like this, capital lambda. Okay, now this relationship can be written in three ways. Here's number one. Just talking our way as to what eigenvector means, we have that. Number two, all depends what you want. If you want to work on A, what did we do? Say I take this V, what do I do with it? Can I cancel this V with that V? No, we said if at the end of the semester you still make that mistake, it's a big problem. How did we get rid of it? I had to multiply by the inverse on that side. It has to be here. So I'm multiplying on the right by V inverse. I have to multiply here also by V inverse. The important thing is that this doesn't cancel that, because that is a problem of linear algebra, or interesting aspect of it. Things do not commute. You can't just move things around. So this is another version of the same story. A third version of this is to say, well, instead of taking this v and bring it here, maybe take this v and bring it on the left. Tell me how to write that one. So in this version, I try to get rid of this v. Okay, tell me, on the right hand side, I want to be left with just a lambda. Now you read out to me what should be written on the left side of this guy. Exactly. So this is v inverse AV. And the way these are written is extremely important. You can't mess with them. It's like it's not open to discussion. You have to multiply by a v inverse on the left of this. And that cancels this v inverse. So you have three versions of this. It is possible to do this if your eigenvectors, first of all, you have n of them, and those n are linearly independent. If they are linearly independent, it means this matrix can be inverted. Like if you were trying to sell me this to be just a couple of that, you wouldn't even be able to find the V inverse. So in some sense, this is more fundamental. This is applicable to any case. Whatever eigenvectors you got, this is fine. Now if you have linearly independent, then V inverse exists. You can put it here or you can put it there. So this is the fundamental relationship, and these are going to come out of that if your matrix V is linearly independent. So this, if you have n linearly independent eigenvectors, over there you can do anything you want because you're not inverting anything. Okay, and then we said, what is the use of this? The use of this is that people subject matrices to all the things you have learned in calculus. Like in calculus, you take something and square it and cube it. You take something, take its tangent, or takes its cosine, take its sine. You can do all sorts of things to a number. You can do all of those things to a matrix. So in calculus, you have learned about functions. Okay, your functions could be sine, cosine, exponential, or whatever. You come to advanced linear algebra, you want to apply those functions to a matrix. First thing that hits you is that this is a very painful thing to do because dealing with matrices are painful. But we said instead of applying it to A, apply it to this one. When we applied to that, what showed up on the right hand side? Let me see if you remember. So you say, okay, instead of applying to A, instead of A, and assuming that your A is a nice matrix, you can instead apply it to V lambda V inverse. Something interesting happens if you do algebra on this. Like if you take lambda V, V lambda V inverse and square it, what do you get? V lambda squared V inverse. Is that right? We practiced that. If you had such a thing and you wanted to cube it, what happens? Everything you want to do just needs to be done to the diagonal matrix lambda. And diagonal matrix is just as easy as an ordinary number. So what happens here, in case this function has a power series expansion, all that you need to do is just to apply it to your eigenvalues. And that is as easy as a breeze. You want to take a sine, well, take a sine. If you want to take cosine, take a cosine. Whatever you want to do, this is no object. So the benefit of all of this pain is that if you want to do algebra on it, you can do it very easily. Now when I ask for diagonalization on a final exam, any of these things would be fine. Well, there's quite a bit of difference between them, that this takes one huge step beyond that, in the sense that you need to find in the inverse. Yeah, so there's a catch there, that there is a difference. For this one, you have to find the inverse of your eigenvector matrix, so that's an additional 10 minutes there already. I'll let you know exactly what is needed. So let me stop this lecture a bit short. Yes, question?
It's called diagonal. The diagonal. What do we call these equations?
They are called diagonalization equations.
Each one doesn't have a specific name.
No, they don't have names. This is you just remember that, and then remember how to move things around, then you're all set. This is giving the A. So this is the, you can think about this as, let's give it them a name so you have an idea what I'm talking about. This is going to be factorization. Okay, so you have a matrix A, you factor it to V, lambda V inverse. Okay, that's clear. Like if I give you a number 15, I tell you factor it, you tell me 3 times 5. Well, this is the most significant factorization we have at the end of this semester. What is it that we had at the beginning of the semester? You remember we had another major factorization? Very big. LU factor, very good. LU factorization, we had, there are many of these factorization in linear algebra, depending on what you want to do. So there are all sorts of factorization. This is factorization in terms of eigenvectors and eigenvalues. This is, what's a good name for this? Well, you think about a good name, and I'll ask you next time. But okay, so we are going to meet, what day is today? Okay, so if you have any questions from any of these things we are doing, make sure you prepare your question, and